and that was to do with magnitudes of element values, concentrations, proximal and distal, and why are they similar.
Yep.
So what I might do then is let you off the hook, and we'll move on to Peter McGoldrick, who has joined us to talk about Lady Loretta.
Thanks, Helen.
No worries.
There we go. That should be the first slide. It's a bit of a disaster scene.
Hold on. Oh, we can't see it yet.
Can't see it yet.
There's a second OK that you've got to press to be able to share the screen.
Right. Which is?
Just try again.
Yeah, I'll try again. All right. So let's share screen. Stop to share. All right.
That looks like it's working. Okay.
It's going to work better. Sorry about that, folks. So that's a bit of a disaster scene. I should mention Vlad's given me a nice segue talking about thallium at Ernest Henry. It's the first time I heard there was thallium anomalism there. And it's an element that's been close to my heart for many years now. And I'll say a little bit more about thallium in sedimentary zinc systems as this brief talk goes on. Now, Rick invited me to do this as a bit of an historical review, because really what I'm talking about is work that was done in the 1990s by a really large team at Codes, and I don't have time to acknowledge them now. They were a couple of major Amira projects, and the Halo study module was a small part of it that Ross Large and I had quite a bit of involvement in. And Lady Loretta was the first one of the case studies that we did. When I got there, this was the state of the little core shed up on the hill at Lady Annie. As you can see, there's lots of grey sticks of core lying around on the ground. These were what were left of the surface drilling that was the discovery or the original ore reserve drilling done from the surface for Lady Loretta. And we had a pretty simple goal in these Halo studies, was what could you do with boring grey siltstone shales with various amounts of sedimentary pyrite in them from a whole rock geochemical point of view to better target or define alteration, whatever that meant, around stratiform sedimentary zinc deposits. And at that point, we got involved in arguments about genesis as well, but the Halo work is largely agnostic towards any sort of models for how the deposits form. So I'm going to very quickly run through the sort of history of what we did at Lady Loretta. Lady Loretta deposit sits in the small syncline that you can see in the northeast on this plan view of the mine. The big syncline has the same mineralised sequence recognised within it, but no significant lead zinc mineralisation. I think there was one small intersection among a dozen or so drill holes, nothing mineable. So that's what we had to deal with in terms of documentation around a small 13 million tonne ore body, a couple of 100 metres long, 10 to 15 metres thick, but lots of drill cores of shale and siltstone on either side. So sort of things you're seeing in the drill core there. There's brown discoloration, so there's hints of siderite or thrown dolomite in those cores. There was a bit known about these, the primary element halos around deposits like Mount Isa. There were studies done going back to the 1960s where things like potassium, maybe, certainly iron enrichment in these rocks. Work on that I did in my PhD in the 80s, there were thallium halos at Mount Isa and HYC. So there were hints that potassium might have been enriched in these sequences as well from CSIRO work by Ian Lambert and others back in the 70s. So there was a little bit known. What you see in a cross-section at Lady Loretta is a well-developed sideritic alteration, both in the hanging wall and the footwall. There's a lot of pyrite in the footwall. There are pyritic interbeds in the hanging wall, and sort of pyrite increases toward the position of the ore, which is the purple shown on this cross section. You could put all that together and come up with a summary of the sort of element patterns you might see in the hanging wall and the footwall of Lady Loretta and perhaps some of our other Northern Australian systems, where there's obviously anomalous zinc up to hundreds or thousands of ppm for a few metres either side of ore. The carbonate composition varies, sideritic at Lady Loretta, anchoritic or Ferrone dolomite in other deposits. Thallium levels of the orders of tens of ppm close to ore, passing away to background levels of a couple, and so on. I won't continue. So that was the sort of state of art with the geochemistry of the rocks and the mineralogy of these boring grey shales. What we were hoping to do, though, was elaborate on this a bit more to come up with the sort of vectoring approach to ore that you're probably all a lot more familiar with in the sort of studies that have been described in today and in earlier vector studies to IOCG systems. And the logic we applied, again, was pretty straightforward. We used the approach that had been used quite successfully in VMS systems, where if you knew what your alteration changes were as you approached ore corresponding to mineralogical or geochemical changes, can you use that information from a chemical point of view to come up with some sort of alteration index? And the Ishikawa index for VMS deposits is looking at the alteration of felspar to sericite and then ultimately chlorite, and it's calculated using a formula that I've left off the diagram. But basically, you're looking at things that are lost, the elements that are lost, elements that are gained. And with a bit of playing around with the geochemical data set we generated for Lady Loretta, perhaps 50 whole rock analyses of grey siltstones and shales from the hanging wall and the footwall. We stayed away from the ore body. We came up with an original alteration index that was measuring or expressing the increase in iron and manganese in the hanging wall and footwall rocks, and comparing that to changes in magnesium and sodium in the rocks as you approach ore. And we ended up having a diagram that compared this alteration index 1, or SEDEX alteration index, we ended up calling it, to the anomalous zinc levels in the rock. And there was a nice trend from what we defined as our background levels, high in the hanging wall and footwall, up to samples that were closer to ore in the siderite halo of the deposit. So we summarised that in terms of something we called a SEDEX trend, where if you're plotting zinc and SEDEX AI, you'd see this curvy linear trend from background to ore if you were in a system that was making a SEDEX lead zinc deposit or a sedimentary lead zinc deposit, whereas rocks that were anomalous in pyrite but otherwise barren would just have expressed the iron increase, but they'd be low zinc. And other types we compared to MVT deposits where there isn't normally the pyrite enrichment, there'd be an MVT trend to high zinc and not much change in SEDEX AI. We then, having recognised manganese was an important element, we assumed that manganese in these dolomitic siltstones and shales was essentially hosted in carbonates, and played around with a simple calculation of re-expressing the whole rock manganese in terms of what that means in terms of the manganese content of the dolomite. So this formula converts the manganese levels in the whole rock to an approximation of the manganese content of dolomite in those rocks. And what that did was it had the effect of smoothing the trend of increasing manganese, particularly in the footwall at Lady Loretta. As you approached ore, there were nice trends in MNOD. So that became an important one of our vectors toward ore, is this MNOD value. Having done that case study, we sort of put it all together and came up with a synoptic diagram of what you might want to look for in drill core that had just missed or was some distance from a Lady Loretta type deposit. We'd be looking at the carbonate alteration. Siderite's good, anchorite's good, dolomite not so much. SEDEX AI values of more than 60. A variation on the SEDEX AI was AI3, and that incorporated aluminium into the denominator of that formula to account for the shaliness or the argillaceousness of your siltstones and shales seem to work a little bit better. We'd be looking at MNOD changes as well. So that was the end of case study 1. We lacked a bit. Actually, I should have said that was ultimately published in a Journal of Geochemical Exploration paper in 1998. And the closest we got to vectoring for Lady Loretta was the idea of being distal or proximal to an ore body using the ZXAI zinc plot. But we were largely constrained at Lady Loretta because the ore body is either faulted or eroded away, and we don't really get a long way from mineralisation. So the second case study we did, and I know it's not in northwest Queensland, but it added that further element of a lateral extent of mineralisation, and it allowed us to work on the world's biggest lead zinc system in terms of halos. That was at HYC. The story for HYC was very similar to Lady Loretta, except the strong development of siderite associated with the immediate hanging wall and footwall of mineralisation wasn't present, but there's certainly iron enrichment and anchorite and ferro and dolomite zoned away from HYC. Again, this work was published a couple of years later, again in Journal of Geochemical Exploration. People are wanting to follow up that story. We added a little bit to the Lady Loretta story, and there is a carbon oxygen isotope story for Lady Loretta as well, but it is expressed better at HYC, where there's a halo of heavy oxygen and somewhat lighter carbon zoned away from the mineralisation at HYC. So there's a trend, we argued, of alteration of the carbonate component of the shales to heavy oxygen and light carbon associated with these sediment-hosted zinc. Sorry about that. Something was saying I wasn't connected, so I hope you've been hearing me.
Yes, we've heard you. Yep.
Did anything happen then?
We just lost your presentation.
Is it back?
Not yet.
Okay. I'll just escape out and try and restart. Just bear with me. Are you seeing my head?
Yep, we can see you.
Okay, so I'll go play again. Is the presentation back?
No. I think you need to reshare the screen.
Okay. I'll do that again. Reshare. Yep, we do need to reshare the screen. Okay. I'm getting close to the end anyhow, so let's see how we go. Play.
Here we go. Yep, we've got it.
All right, so I just fit, these are my last 2 synoptic diagrams of our concept for halos around sedimentary zinc systems by the time we've done a couple of case studies. So there's complexity in these, and not every deposit's going to be exactly the same. There's going to be some elements of each of these overlapping halos in a sedimentary zinc system. And I won't bother to talk through that in the interest of time. The sort of things we'd be looking for, and this is more drawn with a scale on it, with kilometre scale halos developed around ore bodies that are laterally up to a few hundred metres, even in the biggest examples. So we've got local to regional iron manganese carbonate halos, siderite maybe, but certainly anchorite, ferro and dolomite. And then we've got broad primary dispersions of thallium, iron, manganese, light carbon, heavy oxygen, and you can play around with sort of tweaking those iron and manganese enrichments using the alteration index and simply the zinc content of the shales as useful tools. So we finished with what we referred to as a basket of indices that might be applied in an exploration program, and the data behind all this appeared in these 2 major MIRA projects. We did, these are both open file now and available from e-publications at University of Tasmania. If anyone wants to download them, they're several hundred pages and there's lots more than halo studies there. So lots of good nighttime reading if you can't sleep. We did follow up with a number of geochemical studies on other sedimentary zinc deposits. Some were not as comprehensive as the first two, the Lady Loretta and the HYC studies, but we did attempt to get a sense of scale for these halos, looking at different sized deposits and prospects. And all of them seem to manifest some aspects of what I've been talking about. And we concluded that you could make arguments that some of the smaller and sub-economic deposits didn't produce halos that were as strongly defined as the larger deposits. But essentially that was where we finished by the end of the 90s. We were working at a time when getting lots of multi-element geochemistry was quite expensive or non-trivial to get the data that you needed. A lot of things have changed since then. So my concluding slide is just a couple of comments about the last 20 years since this research work's finished, and the way you might be thinking about using these approaches now. Certainly, good, cheap quality analyses, assays are far more readily obtainable, and we've got the tools to really investigate the data from large data sets. And if I can allude back to thallium, when we started this project, getting thallium analyses was extremely difficult and slow and time consuming. By the early 90s, ICP-MS techniques came in, and all of a sudden the ability to measure low-level thallium by the year 2000 was cheap as chips and lots more data, but it was a little bit too late for our project. In the last 20 years, there hasn't been a lot of exploration for new big sedimentary zinc deposits, except by a couple of majors. There's been tightly held ground in parts of the Northern Territory. So I talk about Khaki. Khaki fields a mixture of green fields and brown fields. Anecdotally, some of the bigger companies were applying these, our basket of indices. I don't think we can really claim any discovery success from applying these, but certainly I think there's some use in screening old drill campaigns. Using these would still be worthwhile even today. The other big thing that's changed, obviously, you can get granular in what we've been doing, get down to sort of the mineral phases individually using MLA and laser ablation ICP, and there's a whole world of pyrite chemistry being applied to the Northern Australian systems to some degree since then. And the last couple of points, or the last point really, I think the big change that's happened in looking at what's happening to make these iron and manganese enrichments around the deposits is our understanding of the character of the chemistry of the mid-Proterozoic oceans has undergone a profound change in that the deep oceans during the mid-Proterozoic were ferruginous oceans. So there was iron in the water column, and that puts quite a different complexion on what's going on with the iron enrichment in these rocks. And if you believe that the systems that make the deposits eventually exhale and dump their contents onto the seafloor, whether or not the zinc's formed at or below the seafloor, then the chemistry of the sedimentary host rocks is going to be affected by both the anoxic ferruginous ocean chemistry and its trace element deportment, and the elements that have been contributed by the hydrothermal fluids. So that's my little comment at the end, that I think there's scope to review what we thought perhaps about how the halos formed back in the 90s, with insights from a deeper understanding of what's going on in the water column in the oceans and diagenetically in the sediments in response to that ferruginous Proterozoic ocean. So thanks, I'll stop there.
Thanks very much, Peter. That was great. And we do have a few questions for you, and I'll run through them. We've got two questions, both related to the thallium. So Jessica Gluchowska and Ben Andrew would both like to know what mineral the thallium is hanging out in. Is it in pyrite or something else? And do you also see elevations in cadmium?
So yes, the pyrite, the thallium is in pyrite, but importantly in rocks that aren't particularly pyritic, it's hosted in potassium phases. So it'll be cave feldspars or sericite. So it's one of the explanation for the broad primary dispersion halos of thallium is that it's got this dual chemical character, that it's quite happy in the presence of sulfide, and the ores are full of thallium, but in the absence of a lot of sulfide generation, it'll happily jump into potassium sites in whatever potassium minerals are around. Cadmium was an element that I looked at in my Mount Isa days in my PhD, and I may as well not have bothered, because basically zinc, whatever zinc was doing, cadmium was doing. So yeah, that's a 30-year-old comment, and we didn't bother to reinvestigate cadmium to any great extent. So
no, that's fair. And George Gibson, last question, would like to know.
Hi, George.
Troublemakers, all of you. No. Your publication front page shows basin inversion, but other figures in your talk have a half graben with little or no inversion. When do you think the mineralizing fluids were introduced? Late in the extension or during inversion?
Neither. It's a discussion for another day, and I think it relates in part, at least, to this understanding of the Proterozoic world. There are ways of looking at these sedimentary zinc deposits, and I'm being very circumspect here. I think fundamentally that there's three different explanations. They're the same explanations that have been going around for 30 years. Either the systems are part of the deposits formed during sedimentation, either as exhalations in brine pools or as replacement within the sediment. The systems formed during basin inversion, so late in the basin history, but still pre-deformation, or there's an extreme school that came from James Cook originally that says the deposits are replacement of solid rock. So I would ignore the solid rock replacement explanations. And then with the other two, I think in terms of everything that I see in these systems, I'm quite happy that the parsimonious explanation for the formation of both all the pyrite that's in most of the systems and the lead zinc sulfides fits quite nicely with a seafloor or very shallow sub-seafloor formation for the deposits. So I'm yet to be convinced of early basin inversion, fluid movement, replacement, or deep subsurface formation. And I know that was the model that originated for Century and probably still stands for Century. But I think there's plenty of arguments you can make that Century is just like the other deposits and sin sedimentation.
Well, that's an excellent segue, Peter.